Hello, this is Matt Dean with A Plus College Ready, and today we're going to talk a little bit about stoichiometry. Stoichiometry comes from roots that mean element and measure, or measuring elements. Stoichiometry is the method used to calculate the amounts of reactants and or products formed during a chemical equation or chemical reaction. You can think of stoichiometry almost like a bookkeeping system that allows chemists to quantitatively account for the amounts of reactants and products. To use this system, chemists must start with a balanced, and let me stress that, a balanced chemical equation for the reaction. And you can think of that balanced equation almost like a recipe. If you know the recipe, you can calculate how much product you make from a known amount of reactants. There's two main types of stoichiometry. One of them is composition stoichiometry. And this will let us look at the mass relationships of the elements in a compound. And then there's reaction stoichiometry, which lets us look at the mass relationships between the reactants and the products in chemical reactions. There's some important terms that you have to understand when you're dealing with stoichiometry. One of them is the mole. Remember, the mole is a unit used to count large numbers of things. It's the unit for the amount of a substance. It's a unit that contains 6.02 times 10 to the 23rd particles of a substance. Particles can be atoms, they can be molecules, or formula units if you're talking about a salt, for example. The molar mass is the mass, usually measured in grams, of 1 mole of a substance. The coefficients are the numbers that appear in front of a chemical formula in an equation that are used to balance it. They tend to indicate that either the number of moles or molecules or formula units in the equation. An atomic mass unit, or AMU, is a unit of mass equal to about 1/12 the mass of a carbon-12 atom. It's also roughly equal to the mass of 1 proton or 1 neutron. A mole ratio is a conversion factor that you derive from a balanced equation, and that mole ratio will allow you to convert from moles of one substance in the equation to moles of another substance in the equation. The molecular mass, also sometimes called the molecular weight, is the mass of one molecule of a substance. It's calculated by adding up the atomic masses of each of the elements in the compound multiplied by the number of atoms of that element in the formula. And finally, the formula mass is the sum of the atomic masses of the constituent atoms in an ionic compound. So we're talking about salts on formula masses. One of the things that you're going to have to do in stoichiometry is be able to calculate the molar mass of a substance. First, determine the total atomic or molecular mass of the substance you're working with. For example, if you're dealing with copper metal, pure copper, you look it up in the periodic table. You find that it has one copper atom has an atomic mass of 63.55 AMUs. Therefore, the molar mass of a copper metal is 63.55 grams per mole. In 63.55 grams, there are 6.02 times 10 to the 23rd copper atoms. Let's say you want to find the molar mass of carbon dioxide. You first of all find its molecular mass. Turns out it's 44 AMUs. To calculate that, you take the mass of one carbon atom, 12, plus the mass of 2 oxygen atoms, 16 each. Add those up, you get 44 grams per mole. This is the molar mass. 44 grams of carbon dioxide will contain 1 mole, or 6.02 times 10 to the 23rd molecules of CO2. Let's do the same with potassium oxide. This one's a salt. You find its formula mass by adding up the mass of 2 potassium atoms and 1 oxygen atom, and you get about 94.2 AMUs. Well, that means the molar mass of potassium oxide is 94.2 grams per mole. In 94.2 grams, you will find 6.02 times 10 to the 23rd formula units of potassium oxide. Some important notes about balanced chemical equations. Mass is conserved in every reaction. the mass of the reactants must be equal to the mass of the products. Also, the number of atoms of each element present is conserved in every reaction. If you have 2 hydrogen atoms on the left reactant side, you must also have 2 hydrogens on the product side. This is true for all atoms. The number of molecules or formula units, moles, and even volumes, they're not always conserved. But the mass and the number of atoms of each type of element are always conserved in every type of chemical reaction. So we're first going to look at some what are called composition stoichiometry calculations. Here we're looking at the masses in one particular substance. So let's say we're trying to convert the number of grams of a substance to the number of moles of that substance. And let's say that we're given 86.0 grams of calcium carbonate, and we want to know how many moles are present. So first of all, we need to determine the molar mass of calcium carbonate. We'll add up the mass of 1 calcium, 1 carbon, and 3 oxygen atoms, and we'll end up with a formula mass of 100.09 AMUs. That means the molar mass of calcium carbonate is 100.09 grams per mole. We'll set up a little factor label chart. So essentially we've established a conversion factor. That 100.09 grams of calcium carbonate is equivalent to 1 mole of calcium carbonate. We're going to put our given over here on the top left. We're going to put our conversion factor on the right side. We're going to put the gram portion of the conversion factor on the bottom so that grams will cancel with grams. We're left with moles of calcium carbonate, which is what we're looking for. To finish up the problem, we're going to multiply across the top. We're going to divide by 100.09, and we're going to be left with 0.859 moles of calcium carbonate. That's the number of moles found in 86.0 grams of the substance. So in this next problem, we're converting the number of moles to the mass. Alright, so this time we want to determine the mass of calcium carbonate found in 2.65 moles. So again, we take our given, we write it on the top left-hand corner of our factor label chart. We have to establish a conversion factor. Now we already established in the last problem that the molar mass of calcium carbonate is 100.09 grams. And then that's equivalent to 1 mole. But notice this time, on the right side of our chart, we put the mole portion of that conversion factor on the bottom. We put the gram portion of that conversion factor on the top. We did that so that the moles here will cancel with the moles here. Now we multiply across the top. We don't have anything to divide by on the bottom. So when we multiply this out, we end up with 265 grams of calcium carbonate. That is the mass of 2.65 moles of calcium carbonate. Next, we're converting the number of moles to the number of particles. And remember, particles could be atoms, molecules, or formula units. What you have to remember here is that 1 mole of a substance is equal to Avogadro's number, 6.02 times 10 to the 23rd particles. So in this first problem, we're given 3.06 moles of CO2. We want to know how many particles. In this case, it would be how many molecules, since CO2 is a molecular compound. Our conversion factor is 1 mole of CO2 is equal to Avogadro's number worth of particles, in this case molecules. The mole portion of that conversion factor goes on the bottom so that it will cancel with moles there. We then multiply 3.06 times 6.02 times 10 to the 23rd, and we end up with 1.84 times 10 to the 24th molecules of carbon dioxide. And again, that's the number of molecules of CO2 found in 3.06 moles of the compound. Next, we're asked to find the number of oxygen atoms present in 3.06 moles of CO2. We already found last time that 1 mole of CO2 contains this many molecules of CO2. So we do a factor label, we cancel out moles of CO2 with moles of CO2. Now remember, that gave us if we multiplied 3.06 times 6.02 times 10 to the 23rd, that gave us the number of molecules of CO2. Here we're looking, though, for the number of atoms of oxygen. So if you look at a CO2 molecule, in every one molecule of CO2, there are 2 oxygen atoms. So we established another conversion factor. 1 molecule of CO2, 2 oxygen atoms. The molecule of CO2 portion of that conversion factor goes on the bottom, so it will cancel with molecules here. Now we multiply 3.06 times 6.02 times 10 to the 23rd times 2. We end up with 3.68 times 10 to the 24th. This says molecules of CO2. It should say atoms of oxygen. And let's just write out oxygen atoms. All right, next we're converting from moles to formula units. And we're asked to convert 7.46 moles of potassium oxide to formula units. Remember that a formula unit in an ionic compound is sort of like a molecule. It just doesn't exist as its own individual particle. So there's 6.02 times 10 to the 23rd formula units in 1 mole of an ionic compound, or salt. So here's our conversion factor, 1 mole. Avogadro's number worth of formula units. The mole portion has to go on the bottom so that moles cancel with moles. We multiply across the top, and we end up with 4.49 times 10 to the 24th formula units, in this case of potassium oxide. Now we're asked to find the number of oxygen atoms present in 7.46 moles of potassium oxide. Just like we did before, we're first going to convert from moles to formula units using our same conversion factor. Moles will cancel. We look at the formula for K2O. In each formula unit, there's 1 oxygen atom. So 1 formula unit, 1 oxygen atom. The formula unit portion of the conversion factor goes on the bottom so that formula units will cancel out. We multiply across the top. We end up with 4.49 times 10 to the 24th oxygen atoms. And that's the number of atoms in 7.46 moles of potassium oxide. And again, that's the number of oxygen atoms in 7.46 moles of K2O. Next, we need to talk about a mole ratio. A mole ratio is a conversion factor that relates the amount in moles of any 2 substances included in a balanced equation. You might hear this called the coefficient ratio. It'll allow you to convert from the number of moles of one substance to the number of moles of another substance in that equation. The mole ratio is derived from the coefficients in the balanced equation. So for example, if we looked at this balanced equation, the mole ratio of, let's say, aluminum to oxygen gas would be 4 moles of aluminum to 3 moles of oxygen gas. The mole ratio between aluminum and aluminum oxide would be 4 moles of aluminum to 2 moles of aluminum oxide. And it would probably be better to reduce that down to 2 moles of aluminum to 1 mole of aluminum oxide. The ratio between oxygen and aluminum oxide, 3 moles of oxygen to 2 moles of aluminum oxide. Again, that's called a mole ratio, and it's derived from the coefficients of the balanced equation. Now we're going to look at what are called reaction stoichiometric calculations, or reaction stoichiometry problems. These will allow us to convert from amounts of one substance to amounts of another substance in the same equation. We're going to start with what are called mole-mole calculations. Here we'll be given moles of one thing and asked to convert to moles of something else. So in this problem, we've got 8.5 moles of aluminum oxide, and we want to know how many moles of oxygen gas will be produced. So first of all, we get our balanced equation. We write down our given, 8.5 moles of aluminum oxide. Now we're going to use our mole ratio. We're going to compare aluminum oxide here to oxygen gas here, and that ratio is 2 moles of aluminum oxide to 3 moles of oxygen gas. We place our mole ratio in our factor label chart like so. We put the moles of aluminum oxide portion of that conversion factor on the bottom so that moles of aluminum oxide will cancel with moles of aluminum oxide. We put the moles of oxygen portion on top, we multiply across the top, we divide by the 2 on the bottom, we end up with 12.8 moles of oxygen gas produced when 8.5 moles of aluminum oxide decompose. Let's do another mole-mole problem. So this time we want to know how many moles of aluminum oxide are required to produce 4.6 moles of aluminum metal. So again, we look at our balanced equation. We write down our given. We're trying to figure out how much aluminum oxide we needed to make this 4.5 moles of aluminum. So we get a mole ratio between aluminum and aluminum oxide, 4 moles of aluminum to 2 moles of aluminum oxide, which we're going to reduce down to 2 to 1 mole ratio. The aluminum portion of that conversion factor goes on the bottom so that moles of aluminum cancel with moles of aluminum. The aluminum oxide portion goes on top. We multiply across the top, divide by the bottom, and we end up with 2.25 moles of aluminum oxide. If that decomposes, it will produce 4.5 moles of aluminum metal. So now we're going to do a mole mass calculation. Here we're going to be given the number of moles of a substance and asked to calculate the mass of another substance in the balanced equation. So first of all, let's start with the balanced equation. The problem tells us if 4 moles of nitrogen gas react completely with hydrogen gas, what mass of ammonia is produced. All right, so we're trying to use the amount of nitrogen that we start with to calculate the mass of ammonia produced. So we take our given, 4 moles of nitrogen, write it down on the far left of our chart. We get a mole ratio between nitrogen gas and ammonia, which is going to be 1 mole of nitrogen for every 2 moles of ammonia produced. The nitrogen portion of that conversion factor has to go on the bottom so that moles of nitrogen cancel out. Now if we stopped at this point, we would get moles of ammonia, but we want the mass of ammonia. So next we need to find the molar mass of ammonia. 1 mole of ammonia contains about 17.04 grams of ammonia. So that's another conversion factor. The mole portion has to go on the bottom so that moles of ammonia will cancel out. Now we multiply across the top, divide by the bottom, and we find out that when 4 moles of nitrogen react with extra hydrogen, we'll expect to produce about 136 grams of ammonia gas. All right, now we can go the other way and do what's called a mass mole calculation. So here we're going to be given the mass of a substance and asked to calculate the number of moles of another substance in the balanced equation. So we're working with that same equation we used in the previous problem. This time, we're given 24 grams of nitrogen gas reacting with hydrogen. We want to know how many moles of ammonia are produced. So we take our given, 24 grams of nitrogen, write it down in the top left. We're trying to get from grams of nitrogen to moles of ammonia. So typically, if we're trying to convert from one thing to another thing, you're going to need to get to moles first. So we're going to take the molar mass of nitrogen gas, 28.02 grams. That's the number of grams in 1 mole of N2. The grams portion goes on the bottom of our dimensional analysis chart, so it'll cancel out. Now we're going to use the mole ratio to convert from moles of nitrogen to moles of ammonia. And if we look at our balanced equation, for every 1 mole of nitrogen that we start with, we produce 2 moles of ammonia. The nitrogen portion of that mole ratio goes on the bottom so that it'll cancel. Now we multiply across the top. We divide by the 28.02 on the bottom, and we expect to produce 1.71 moles of ammonia if we start with 24 grams of nitrogen gas. All right, next we're going to do a mass calculation. In this kind of problem, we're given the mass of one substance, and we're using that balanced equation to calculate the mass of another substance in the equation. So this time we're working with this particular balanced equation. We're given 20 grams of copper reacting completely with sulfur to produce copper 2 sulfide. So we start with our given. We're first going to use the molar mass of copper to convert from grams of copper to moles of copper. We have to put the grams portion of that conversion factor on the bottom so it'll cancel. Next, we use the mole ratio from the balanced equation. And we can see that for every 2 moles of copper that we start with, we should make 1 mole of copper 2 sulfide. I'm sorry, copper 1 sulfide is what we're dealing with here, copper 1 sulfide. So 2 moles of copper need to go on the bottom so that moles of copper cancel with moles of copper. 1 mole of copper 1 sulfide on top. Finally, we've got to go back to mass of copper 1 sulfide, so we need to use the molar mass of copper 1 sulfide, which is 161.16 grams. We put the mole portion of our conversion factor on the bottom so it will cancel. We multiply across the top. We divide by everything on the bottom, and we end up with 25.0 grams of copper 1 sulfide produced if we start with 20 grams of copper metal and it reacts completely with sulfur. So now we're going to do some calculations involving the volume of a gas. And what you have to know here is that 1 mole of any gas, doesn't matter what kind of gas, has a volume of 22.4 liters. As long as it's taking place, the reaction is taking place at STP, standard temperature and pressure, which for gases is 0 degrees Celsius for temperature and 1 atmosphere for pressure. So we're assuming at STP. This is not true, this relationship is not true if the temperature or pressure, or both, are not at STP. So here we're going to start with 24 grams of nitrogen gas, and we're reacting with hydrogen gas at STP. We want to know what volume of ammonia is produced. So we've got a balanced equation. We start with 24 grams on our upper left-hand side of our formula chart, for our factor label chart. We're first going to use the molar mass of nitrogen gas to convert that to moles. The grams portion of that conversion factor goes on the bottom, so we can cancel out grams. Next, we're going to use the mole ratio. The mole ratio between nitrogen and ammonia is 1 to 2. The nitrogen portion of that mole ratio has to go on the bottom of our chart, so it can cancel. The 2 moles of ammonia go on top. And finally, we want to convert from moles of ammonia to liters, volume of ammonia. Remember, we're at STP, so 1 mole of ammonia is equal to 22.4 liters of ammonia. The moles here and the moles here cancel out. We multiply across the top and divide by the bottom, and we end up with 38.4 liters of ammonia. All right, so here's another problem dealing with volume of gases at STP. So here we want to know what mass of nitrogen is required to produce 30.2 liters of ammonia at STP. So we're sort of doing the opposite of what we did in the last problem. We take our given, write it down first. This time we're going to use the relationship of 22.4 liters is equal to 1 mole. Remember, that only works at STP, but liters cancel. Now we're going to use the mole ratio from our equation. 2 moles of ammonia for every 1 mole of nitrogen that we started with. This time the ammonia portion of that conversion factor has to go on the bottom so that these moles here cancel with these moles here. The nitrogen portion goes on top. And then finally we're going to convert back to grams, remembering that 1 mole of nitrogen is equal to 28.02 grams of nitrogen. We have to use the formula mass. Multiply across the top, divide by the bottom, and we end up with 18.9 grams of nitrogen gas. Next, we're going to talk about the limiting reactant. A limiting reactant is a reactant that limits or determines the amount of product formed during a chemical reaction. The limiting reactant is completely consumed by the reaction. Once this happens, no more product can form. You might also hear the limiting reactant called the limiting reagent. The excess reactant, on the other hand, is the reactant or the reactants that are not completely consumed during a reaction. Once all of the limiting reactant is consumed, the reaction stops, and the excess reactants are going to be left over. There's going to be some of those left behind. Let's say that a recipe called for, to make a cake, called for 4 eggs and 2 cups of sugar. Well, let's say you have 2 cups of sugar, but you have 6 eggs. The cup of sugar is your limiting reactant. For 1 cup of sugar, you need 4 eggs. Well, you have 4 eggs, but you've also got 2 extra ones. So the eggs are the excess reactant. The sugar is the limiting reactant. Once you've made that cake, you're going to have 2 eggs left over in excess. So, to do stoichiometry problems involving limiting reactants, you first have to determine what the limiting reactant is. So in this case, we're asked to determine the limiting reactant when 24 grams of nitrogen gas react with 8 grams of hydrogen gas according to the balanced equation below. So the same equation we've used in the last couple of problems. We're first going to convert the mass of either of the reactants to moles. And then we're going to use the molar masses and get a mole ratio to determine how much of one of the reactants we need to go with the other reactant. For example, let's say we started with the 24 grams of nitrogen. And we just as easily could have started with the 8 grams of hydrogen. It doesn't matter which one you start with. Let's use the molar mass of nitrogen to convert from grams of nitrogen to moles of nitrogen, canceling out the grams. Now let's use a mole ratio. For every 3 moles of hydrogen, we need 1 mole of nitrogen. The nitrogen portion of that ratio goes on the bottom so that moles of nitrogen cancel. Hydrogen portion goes on top. Now let's use the molar mass of hydrogen gas, 2.02, 2.02 grams per mole, to convert from moles of hydrogen to grams of hydrogen. We end up with 5.19 grams of hydrogen. So what that tells us is that for 24 grams of nitrogen, we need 5.19 grams of hydrogen to go with it. Well, we have more than 5.19 grams of hydrogen. We have 8 grams of hydrogen. That means that hydrogen is our excess reactant, and therefore nitrogen must be the limiting reactant. So next we're going to use the limiting reactant to determine a certain amount of product that will form. In this case, though, we were only asked to determine the limiting reactant. So our answer here is that nitrogen is the limiting reactant. Now we're asked to work the same problem, but start with hydrogen. So we're starting with 8 grams of hydrogen. We use the molar mass of hydrogen to convert from grams of hydrogen to moles of hydrogen. We use a mole ratio of 3 moles of hydrogen to 1 mole of nitrogen. Remember, that came from our equation. And then we use the molar mass of nitrogen gas, 28.02 grams per mole. We do the math. We multiply across the top. We divide by the bottom. And we get 37.0 grams of nitrogen. So if we used all of our 8 grams of hydrogen, we would need 37 grams of nitrogen to go with it. We don't have 37 grams of nitrogen. We only have 24. That again means nitrogen is the limiting reactant. Hydrogen, on the other hand, is the excess reactant. When this reaction is over, all the nitrogen will be used up. There will be some hydrogen left over. All right, so now we've got a problem. We're going to use the limiting reactant to determine the amount of product formed. So again, we're working with the same equation. This time we're starting with 24 grams of nitrogen and 8 grams of hydrogen, and we want to know the mass of ammonia formed. So just like we did before, or what we would do, it would be what we did before. We would first determine the limiting reactant. We already determined that the limiting reactant is the nitrogen gas. The limiting reactant determines the amount of product formed. So we can sort of forget about the amount of hydrogen here. That's in excess. We're going to use the 24 grams of nitrogen, our limiting reactant, to determine the amount of product formed. So we're going to start with the amount of limiting reactant that we have. We're going to convert that to moles using the molar mass of nitrogen gas. Grams cancel. We're going to do a mole ratio. For every 1 mole of nitrogen that we started with, we're going to create 2 moles of ammonia. The nitrogen portion of that goes on the bottom, so it'll cancel. 2 moles of ammonia on top. Next, we use the molar mass of ammonia. 1 mole is 16.03 grams. And we convert to grams of ammonia. We end up with 27.5 grams of ammonia produced when 24 grams of nitrogen react with 8 grams of hydrogen gas. Rice tables can also be used to work limiting reactant problems. Rice tables are a way to, like I said, solve limiting reactant stoichiometry problems. They're used to organize the information for stoichiometry with a reaction, and they help us to set up the equations that are necessary to solve for certain unknowns. All the numbers in a rice table should be in moles. If you're asked to find volume, which you may be in some problems, or mass, you're going to have to do some steps outside of the table. RICE is an acronym. The acronym stands for R, stands for the balanced reaction or the balanced equation. I stands for the initial conditions, what you have before the reaction happens. C stands for the change that happens as the reaction takes place. Reactants are used up or removed, while products are made or formed. And then E are the end conditions, what you have after the reaction is over. All right, so we're going to use a rice table to work the problem we just previously worked. Remember, we were asked to determine the mass of ammonia formed when 24 grams of nitrogen gas react with 8 grams of hydrogen gas according to this equation. So the first thing we're going to do is set up the rice table. We start with our balanced equation across the top, as you see here. We put 1 reactant or product per column. Over here on the left side, we have our RICE acronym, initial, change, and end. You'll sometimes hear these tables called ICE tables instead of RICE tables. Also, we're going to use the coefficients from the balanced equation to determine the relative amount of change. So if there's a coefficient of 2, we're going to have a change of 2x. If there's a coefficient of 3, we're going to have a change of 3x. Also, remember that reactants decrease in amounts, so we're going to put negative numbers for those, while products will increase, we're going to put positive numbers for those. So notice our coefficient in front of nitrogen is 1, it's a reactant, so minus 1x. Our coefficient in front of hydrogen is 3, it's a reactant, so minus 3x. And our coefficient in front of ammonia is 2, it's a product, so we're going to have plus 2x. So step 2, remember, moles are the only things allowed in the rice table. We want to find the moles of each reactant, and we want to insert those into the I box, the initial conditions box. Remember, there's no moles of product to begin with because we haven't made the product yet. So we're just going to put some dashes in the product I boxes. So the first thing that we needed to do was to convert 24 grams of nitrogen and 8 grams of hydrogen to moles. So as you can see, I already did that down here. It's 0.857 moles of nitrogen and 3.96 moles of hydrogen. And you can see that I entered dashes for the initial number of moles of ammonia. Step 3 is to find X. Remember, one of the reactants is going to be the limiting reactant, which means we're going to run out of it. And we're going to have leftover amounts of the other reactant. There's two possibilities for this. If nitrogen runs out, then the 0.857 moles minus X is going to be 0. That means all the moles of nitrogen are used up. Therefore, X would be 0.857. On the other hand, if hydrogen is the limiting reactant and it runs out, 3.96 minus 3x, remember that 3 comes from our balanced equation, would equal 0. And therefore, X is going to be equal to 3.96 divided by 3, which is 1.32. Whichever one of these two calculations gives us the lowest X value, that's going to be the limiting reactant. So in this case, nitrogen has the lowest X value. It's going to be the limiting reactant. So once we get the limiting reactant, we're going to go ahead and fill in using our X values. And you can see I'm doing that in the change row. So remember, our coefficient there was negative 1x. So I multiplied negative 1 times 0.857 and got negative 0.857. In the hydrogen column, I had negative 3x. So negative 3 times 0.857 gave us negative 2.571. And in the nitrogen column, or the ammonia column rather, right here, I had plus 2x. So 2 times 0.857. Step 5, now we solve for everything. And we do that by adding up everything down each column. So we'll add up positive 0.857 and negative 0.857 to get 0. That means when the reaction's over, all of our nitrogen has been used up. Here we're going to take 3.96 plus negative 2.571, and we get 1.39 moles. That means this amount of hydrogen is in excess. It's left over. We didn't use that much of the hydrogen. And then we add up this column. It shouldn't be really anything to add up here. This is the number of moles of ammonia that we made during this reaction. Now we're going to answer the question. Our table has pretty much all the information that we'll need. It has, remember, the number of moles of everything. This question asks us to find the mass of ammonia produced. Mass is asking us for grams. We know that we produced this many moles of ammonia, so we need to convert that number of moles of ammonia to grams. The molar mass of ammonia is 16.03 grams per mole. So we do the math. Our answer, exactly what we got when we worked this problem using dimensional analysis, is 27.5 grams of ammonia. So that's using a rice table to work a limiting reactant problem. All right, here's a different problem. This time we're working with this equation. And we want to know what mass of aluminum chloride is produced when 90 grams of aluminum metal react with 75 grams of chlorine gas. So first of all, we need to determine what the limiting reactant is. We can start our calculation with either the 90 grams of aluminum or the 75 grams of chlorine gas. It doesn't matter. But we've got to determine what the limiting reactant is. I'm going to start with the aluminum. And I'm first going to convert the 90 grams of aluminum to moles using the molar mass. Grams cancel. I'm going to do a mole ratio between my chlorine and aluminum, which is going to be 3 to 2 moles. The 2 moles of aluminum cancel out there. And then I'm going to use the molar mass of chlorine gas. 1 mole is 70.91 grams. I'm going to multiply across the top and divide by the bottom and get 355 grams. That tells me that if I start with 90 grams of aluminum, I need 355 grams of chlorine to react with it. I only have 75 grams of chlorine. I don't have as much as I need. That tells me that chlorine is the limiting reactant. When this reaction is over, there's going to be a lot of aluminum left over. Aluminum is in excess. So now I'm going to have to use my amount of chlorine, my 75 grams, and I'm going to use that to determine how much aluminum chloride will be made. Remember, the limiting reactant determines the amount of product formed. So I'm going to start with my 75 grams of chlorine. I'm going to use the molar mass of chlorine to convert from grams to moles. I'm going to use the mole ratio between chlorine and aluminum chloride, which from my equation was 2 moles of aluminum chloride to 3 moles of chlorine gas. The moles of chlorine cancel. And then I'll use the molar mass of aluminum chloride to convert from moles of aluminum chloride to grams. And when it's all said and done, I end up with 94 grams of aluminum chloride produced when 90 grams of aluminum metal react with 75 grams of chlorine gas. Let's also talk about percent yield. Percent yield is a measure of the efficiency of a reaction. You calculate it by the percent yield is equal to the actual yield divided by the theoretical yield times 100%. The actual yield is the amount of product that you actually obtain when you do the reaction in the lab. You weigh it out, you measure it out. The theoretical yield is the amount of product that you calculated that you should make. That came from your stoichiometry calculation. You're never going to get as much as you theoretically should get. So your percent yield should always be less than 100% unless you do something wrong in the lab. So let's look at a problem. What's the percent yield if 20.2 grams of calcium oxide is obtained when 60 grams of calcium carbonate are heated and decomposed according to the chemical equation included below? So here's our balanced equation. We're starting with we're making 20.2 grams. So that's going to be our actual yield. That's how much we actually got when we did this experiment. We know we're starting with 60 grams of calcium carbonate. So let's take that 60 grams. Let's use the molar mass of calcium carbonate to convert from grams to moles. Let's do a mole ratio between calcium carbonate and calcium oxide, 1 to 1. And let's convert from moles of calcium oxide to grams of calcium oxide using the molar mass. Here's the molar mass. This number is our theoretical yield of calcium oxide. This is how much the math says we should get when we decompose 60 grams of calcium carbonate. When we actually did the experiment, though, we only got 20.2 grams. So to calculate the percent yield, we take our actual yield, which was 20.2 grams. We divide it by our theoretical yield, 33.6 grams. Grams cancel out. We multiply by 100%, and we end up with a percent yield of about 60.1%. If you're a chemist, you want your percent yield to be high because you're wasting reactants if you have a very low percent yield. You want as high of a percent yield as possible, assuming you're using this reaction to make some product that you then want to sell. All right, that's it for stoichiometry. I hope that helped.